Having discussed RNNs last week, we'll now move to a topic which is very contemporary in terms of trying to address some of the technical features of what RNN brings to deep learning, which is attention models. Before we go into attention models, let's discuss the question that we left behind, which was, what do you think will happen if you train a model on normal videos and do inference on a reversed video? Hope you had a chance to think about this. It depends on the application or task. For certain activities, let's say you want to differentiate walking from jumping, it could work to a certain extent even if you tested it on a reversed video. However, for certain other activities, say a sports action such as a tennis forehand, this may not be that trivial. An interesting related problem in this context is known as finding the arrow of time. There are a few interesting papers in this direction where the task at hand is to find out whether the video is forward or backward. This can be trivial in some cases, but this can get complex in some cases. If you're interested, please read this paper known as Learning and Using the Arrow of Time if you'd like to know more. So far with RNNs, we saw that RNNs can be used to efficiently model sequential data. RNNs use backpropagation through time as the training method. RNNs, unfortunately, suffer from the vanishing and exploding gradients problems. To handle the exploding gradient problem, one can use gradient clipping, and to handle the vanishing gradients problems, one can use RNN variants such as LSTMs or GRUs. Which was good. We saw how to use these for handling sequential learning problems. But the question we ask now, is this sufficient? Are there tasks when RNNs may not be able to solve the problem? Let's find more about this. Let's consider a couple of popular tasks where RNNs may be useful. One is the task of image captioning. Given an image, one has to generate a sequence of words to make a caption that describes the activity or the scene in the image. Another example where RNNs are extremely useful is the task of neural machine translation, or what is known as NMT. It's also what you see on your translate apps that you may be using, where you have a sentence given in a particular language and then you have to give the equivalent sentence in a different language. Both of these are RNN tasks. A standard approach to handling such tasks is, given any input, your input could be video, could be an image, could be audio, or could be text. You first pass these inputs through an encoder network, which gets you a representation of that input, which we call the context vector. Given this context vector, you pass this through a decoder network, which gives you your final output text. These are known as encoder-decoder models, and they are extensively used in such a context. Now let's take a brief detour to understand encoder-decoder models a bit more. The standard name for such encoder-decoder models is known as the autoencoder, although in this case it says that the decoder is trying to encode the input itself, and that's the reason why this is called an autoencoder. Not all encoder-decoder models need to be autoencoders. However, the conceptual framework of encoder-decoder models comes from autoencoders, which is why we're discussing this briefly before we come back to encoder-decoder models. An autoencoder is a neural network architecture where you have an input vector, you have a network which we call as the encoder network, and then you have a concept vector, or we also call that the bottleneck layer, which is a representation of the input, and then you have a decoder layer or a network which outputs a certain vector. In an autoencoder, we try to set the target value to the input themselves. So you're asking the network to predict the input itself. So what are we really trying to learn here? We're trying to learn a function f parameterized by some weights and bias wb. F of x is equal to x. Rather, we are trying to learn the identity function itself and predict an output x hat which is close to x. So how would you learn such a network? Using backpropagation. What kind of a loss function would you use? It would be a mean squared error where you're trying to measure the error between x and x hat, which is the reconstruction of the autoencoder. Then you can learn the weights in the network using backpropagation as with any other feed-forward neural network. Now, the encoder and the decoder need not be just one layer. You could have several layers in the encoder. Similarly, several layers in the decoder. In the autoencoder setting, traditionally, the decoder is a mirror architecture of the encoder. So if you have a set of layers in the encoder with a certain number of dimensions, number of hidden nodes in each of these layers, then the decoder mirrors the same architecture the other way to ensure that you can get an output which is of the same dimension as the input. That's when you can actually measure the mean square error between the reconstruction and the input. However, while this is the case for an autoencoder, not all encoder-decoder models need to have such architectures. You can have a different architecture for an encoder and a different architecture for a decoder depending on what task you're trying to solve. Just to understand a variant of the autoencoder, a popular one is known as the denoising autoencoder. In a denoising autoencoder, you have your input data. You intentionally corrupt your input vector. For example, you can add something like a Gaussian noise and you would get a set of values x1 hat to xn hat. So those are your corrupted input values. Now you pass this through your encoder, you get a representation, then a decoder, and you finally try to reconstruct the original input itself. What is the loss function here? The loss function here would again be mean squared error. This time it would be the mean squared error between your output and the original uncorrupted input. What are we trying to do here? We are trying to ensure that the autoencoder can generalize well tomorrow at the end of training so that even if there was some noise in the input, the autoencoder would be able to recover your original data. With that introduction to autoencoders, let's ask one question. In all the architectures that we saw so far with autoencoders, we saw that the hidden layers were always smaller in size in dimension when compared to the input layer. Is this always necessary? Can you go larger? Autoencoders where the hidden layers have a lesser dimension than the input layer are called undercomplete autoencoders. So you can say that such autoencoders learn a lower dimensional representation on a suitable manifold of input data, from which if you use the decoder, you can reconstruct back your original input. On the other hand, if you had an autoencoder architecture where the hidden layer dimension is larger than your input, you would call such an autoencoder as an overcomplete autoencoder. While technically this is possible, the limitation here is that the autoencoder could blindly copy certain inputs to the certain dimensions of that hidden layer which is larger in size and still be able to reconstruct, which means such an overcomplete autoencoder can learn trivial solutions which don't really give you useful performance. They may simply memorize all the inputs and just copy inputs back to the output layer. Then the question is, are all autoencoders also dimensionality reduction methods, assuming we are talking about undercomplete autoencoders? Partially yes. Largely speaking, autoencoders can be used as dimensionality reduction techniques. A follow-up question then is, then can an autoencoder be considered similar to principal component analysis, which is a popular dimensionality reduction method? The answer is actually yes again, but I'm going to leave this for you as homework to work out the connection between autoencoders and PCA. Let's now come back to what we were talking about, which was one of the tasks of RNNs, which is Neural Machine Translation, or NMT. These kinds of encoder-decoder models are also called sequence-to-sequence models, especially when you have an input to be a sequence and an output also to be a sequence. So if you had an input sentence which says India got its independence from the British, let's say now that we want to translate this English sentence to Hindi, what you would do now is you would have an encoder network which would be a recurrent neural network, an RNN, where each word of your input sentence is given at one time step of the RNN, and the final output of the RNN would be what we call a context vector, and this context vector is fed into a decoder RNN which gives you the output which says Bharat ko, the rest of the sentence, mili, and then you have an end of sentence token. This is what we saw as a many-to-many RNN last week. Why aren't we giving an output at each time step of the encoder RNN? For a machine translation task, if you recall the recommended architecture, we said that it's wiser to read the full sentence and then start giving the output of the translated sentence. Why so? Because different languages have different grammars and sentence constructions. So it may not be correct for the first word in English to be the first word in Hindi, or the Hindi sentence may not exactly follow the same sequence of words in English because of grammatical regulations. So that's the reason why in machine translation tasks, you generally have a reading of the entire input sentence, you get a context vector, and then you start giving the entire output in the translated output. Similarly, if you considered the image captioning task, you would have an image, and in this case, your encoder would be a CNN followed by, say, a fully connected network, out of which you get a representation or a context vector, and this context vector goes to a decoder which outputs the caption, a woman ... say in the park, end of sentence. What's the problem? This seems to work well. Is there a problem at all? Let's analyze this a bit more closely. So in an RNN, the hidden states are responsible for storing relevant input information in RNNs. So you could say that a hidden state at time step t or ht is a compressed form of all previous inputs. That hidden state represents some information from all the previous inputs which is required for processing in that state as well as future states. Now let's consider a longer sequence. If you considered language processing and a large paragraph, if your input is very long, can your HT, the hidden state at any time step, encode all this information? Not really. You may be faced with the information bottleneck problem in this kind of a context. So if you considered a sentence such as this one here, which has to be translated to German, can we guarantee that a words seen at earlier time steps be reproduced at later time steps? Remember, when you go from a language such as English to a language such as German, the position of the verbs, the nouns may all change, and to reproduce this, one may have to get a word much earlier in the sentence in English, which may follow much later in, say, the German language. Is this possible? Unfortunately, RNNs don't work that well when you have such long sequences. Similarly, even if you had image captioning and related problems such as visual question answering, which we will see later. So if you had this image that we saw in the very beginning of this course, and if we asked the question, what is the name of the book? The expected answer is the name of the book is Lord of the Rings. The relevant information in a cluttered image may also need to be preserved in case there are follow-up questions with a dialogue. So a statistical way of understanding this is through what is known as BLUE score. BLUE score is a common performance metric used in NLP, natural language processing. BLUE stands for Bilingual Evaluation Under Study. It's a metric for evaluating the quality of machine translated text. It's also used for other tasks such as image captioning, visual question answering, so on and so forth. And when one looks at the BLUE score, one observes that as the sentence length increases, then while the expected curve is that you should get a high BLUE score after a certain sequence length, unfortunately, as the sentence length goes further beyond a threshold, the BLUE score starts falling down. Which means using such encoder-decoder models, where encoders are RNNs, decoders are also RNNs, starts failing in these cases when the sequences are long by nature. If you'd like to know more about BLUE, you can see this entry in Wikipedia for more information. So what is the solution to this problem? The solution, which is extensively used today, is what is known as attention, which is going to be the focus of this week's lectures. So what is this attention? Intuitively speaking, given an image, if we had to ask the question, what is this boy doing? The human way of doing this would be, you first identify the artifacts in the image. You pay attention to the relevant artifacts, in this case the boy and what activity the boy is associated with. Similarly, if you had an entire paragraph and you had to summarize, you would probably look at certain parts of the paragraph and write them out in a summarized form. So paying attention to parts of inputs, be it images or be it long sequences like text, is an important way of how humans process data. So let's now see this in a sequence learning problem in the traditional encoder-decoder model setting. So this is once again the many-to-many RNN setting, similar to what we saw for neural machine translation. So you have your inputs, then you have a context vector that comes out at the end of the inputs. That context vector is fed to a decoder RNN, which gives you the outputs y1 to yk. Now let's assume that hj's are the hidden states of the encoder and sj's are the hidden states of the decoder. So what does attention do? Attention suggests that instead of directly outputting ht, which is the last hidden state, to your decoder RNN, we instead have a context vector which relies on all of the hidden states from the input. This creates a shortcut connection between this context vector ct and the entire source input x. How would you learn this context vector? We will see there are multiple different ways. So given this context vector, the decoder hidden state st is given by some function f of st minus 1, the previous hidden state in the decoder, yt minus 1, the output of the previous time step in the decoder could be given as input to the next time step, as well as the context vector ct. And what is this context vector? This context vector is given by ct, which is over all the time steps in your encoder RNN, alpha tj hj. So it's a weighted combination of all of your hidden state representations in your encoder RNN. How do you find alpha tj? How do you find those weights of the different inputs? A standard framework for doing this is alpha tj can be obtained as a softmax over some scoring function that captures the score between st minus 1 and each of the hidden states in your encoder. So st minus 1 gives us a current context of the output. So we try to understand what is the alignment of the current context in the output with each of the inputs and accordingly pay attention to specific parts of the inputs. Now there's an open question. How do you compute this score of st minus 1 with each of the hj's in the encoder RNN? Once we have a way of computing that score, we can take a softmax over hj with respect to all of the hj's. So we would do this for each of the hj's in the encoder RNN. And using that, we can compute your alpha tj's, and using alpha tj's, we can compute the context vector. Once you get the context vector, you would give the corresponding context vector as input to each time step of the decoder RNN. How do you compute this score? There are a few different approaches in literature at this time. We will review many of them over the lectures this week. But to give you a summary, you could have a content-based attention which tries to look at st and hi. So each a particular hidden state in your decoder RNN st and a particular hidden state in an encoder RNN hi as a cosine similarity between the two. That's one way of measuring the score. You could also learn weights to compute this alignment. So you can take st and hi, learn a set of weights wa, take a tan h and use another vector to get the score. So this is a learning procedure to get your final score. One could also get alpha tj as a softmax over a learned set of weights w and st again. One could also use a more general framework where you have ST transpose HI, which is similar to cosine, which will give you a dot product, but you also have a learned set of weights in between, which tells you how to compare the two vectors ST and HI. Remember, any W here are learned by the network to compute the score. Or you could simply use just a dot product by itself, which would be similar to your content-based attention. The cosine and the dot product would give similar values. Or there is a variant known as the scaled dot product attention, where you use the dot product between the two vectors ST and HI, but scale it by root n, which tells you the number of inputs that you have. What about spatial data? So we saw how it is done for temporal data, where you had a sequence to sequence RNN, a many to many RNN. What if you had an image captioning task? If you had spatial data. So in this case, your image would give you a certain representation S0 out of the encoder network. Unfortunately, when you use a fully connected layer after the CNN, you lose spatial information in that vector. So instead of using the fully connected layer, we typically take the output of the convolutional layers themselves, which would give you a certain volume, which let's say is m cross n cross c. Now we know that if you considered one specific patch of this volume m cross n cross c, we know that you can trace that back to a particular patch of the original image which was passed through a CNN. So you know that the output feature map, say a conv5 feature map, if you looked at one particular part of that depth volume, you would get a certain patch in the input image. Now this gives you spatial information. So what can we do? We take this feature map that we get at the output of a certain convolutional layer, we can unroll them into 1 cross 1 cross c vectors. So you ideally have m cross n cross c. So you can unroll this into c different vectors, and then you can apply attention to get a context vector. In what way is this useful? This context vector now can be understood as paying attention to certain parts of the image while giving the output, because each of these bands, each of these sub-volumes here highlighted in yellow are certain parts of the input image, and one could now understand the same weighted attention concept. The alignment part of it could be implemented very similar to what we saw on the previous slide, but now this represents different parts of the input image. Another use of performing attention is it gives you explainability of the final model. Why so? How so? If you have, say, a machine translation task, you know that when you generated a certain output word from a decoder RNN, your attention model or your context vector tells you which part of the input you looked at while predicting that word as the output, and that automatically tells you which words in your input sequence corresponded to a word in your output. So in this case, you can see that this particular sequence here, European Economic Area, depended on Zone Economic European. So that is also highlighted by these white patches here. So white means a higher dependence, black means no dependence. And looking at this heat map gives you an understanding of how the model translated from one language to another. What about images, image captioning task? In this case too, you can use the same idea. Given an image, if the model is generating a caption, you can see that the model generates each word of the caption by looking at certain parts of the image. For example, when it says a, it seems to be looking at a particular part of the image. When it says a woman, it seems to be looking at a certain part of the image while the other object is also in relevance. And if you keep going, you see when it says the word throwing, it seems to be focusing on the woman part of the image. And if you see the word frisbee, it actually seems to focus on the frisbee in the image. And if you see the word park, it seems to be focusing on everything other than the woman and the child. This gives you an understanding and trust that the model is looking at the right things while giving a caption as output. What are the kinds of attention one can have? You could consider having a hard versus soft attention. What do these mean? In hard attention, you choose one part of the image as the only focus for giving a certain output. Let's say image captioning. You look at only one patch of the image to be able to give a word as an output. So this choosing of a position could end up becoming a stochastic sampling problem, and hence one may not be able to backpropagate through such a hard attention problem because that stochastic sampling step could be non-differentiable. We will see this in more detail in the next lecture. On the other hand, one could have soft attention where you do not choose a single part of the image, but you simply assign weights to every part of the image. In this case, you are only going to have a newer image where each part of the image has a certain weight. In this case, your output turns out to be deterministic, differentiable, and hence you can use such an approach along with standard backpropagation. Another categorization of attention is global versus local attention. In global attention, all the input positions are chosen for attention, whereas in local attention, maybe only a neighborhood window around the object of interest or the area of interest is chosen for attention. A third kind, which is very popular today, is known as self-attention, where the attention is not with respect to an decoder RNN with respect to the encoder or an output RNN with respect to parts of an image, but is of attention of a part of a sequence with respect to another part of the same sequence. This is known as self-attention or intra-attention, and we'll see this in more detail in a later lecture this week. Your homework for this lecture is to read this excellent blog by Lillian Weng known as Attention. It's a blog on GitHub. And one question that we left behind, which is there a connection between an autoencoder and principal component analysis? Think about it, and we'll discuss this in the next lecture. References.